Welcome to the Advanced Software Architecture course. My name is Michel Chaudron and this is the lecture Introduction to Architecture Part 2. This lecture contains an overview of the most important conceptual building blocks that are the foundation of software architecture. Moreover, we discuss different types of stakeholders and their different types of needs, and we will discuss tasks that could be assigned to the software architect. A software architecture is a set of architectural elements that have a particular form. Elements could be either processing data or connecting elements, and the processing elements are those components that supply the transformation on the data elements. The data elements are those that contain the information that is used and transported, while the connecting elements transport data between components. For example, procedure calls, share data, and messages are different examples of connecting elements that serve to glue together architectural elements. Architectural form is related with the composition and distribution of these elements. It addresses the configuration or the topology as well as the relationship amongst the elements with their environment. Thirdly, there's rationale and constraints. They address the designer's intent, assumptions, and external constraints. A rationale is an integral part of an architecture. The rationale captures the motivation for the choice of architectural style, the choice of elements, and the choice of form. In software architecture, the rationale explicates the satisfaction of the system constraints. The rationale provides the underlying basis for the architecture in terms of constraints which often derive from system requirements. Key software elements. Component-based software engineering is a branch of software engineering that emphasizes the modularity and composability of software systems. It is an approach to defining, implementing, and composing loosely coupled independent components into systems. We distinguish three different classes of architectural elements that are of importance when talking about architectural designs. Processing, which may also be referred to as functionality, it relates to what is computed. Then there is the state, which refers to the information or data. And then there is interaction or communication. This deals with how two or more software components interact. It may also be referred to as interconnection, communication, coordination, or mediation. Elements that encapsulate functionality and data in a systems architecture are referred to as software components. Components are in charge of processing or storing data, or both. Another fundamental aspect of software systems is the interaction between the system's building blocks. And software connectors are the architectural abstraction that represents such interaction between components. Key software elements. The software architecture of a program or computing system is the structure of the system, which comprises software elements. Architecture focuses on how the major elements within an application are used by or interact with other components within the application. The example on this slide presents the key software elements. Components, interfaces, and connectors. Each of these elements will be separately addressed in the following slides. Component. Components are the architectural building blocks that encapsulate a subset of the system's functionality and/or data and restrict access to them via an explicitly defined interface. Ideally, a component is modular, portable, replaceable, and reusable. Moreover, a component encapsulates its implementation and exports it as a high-level interface. component has clearly defined interfaces and conforms to a recommended behavior common to all components within an architecture. A common example of a definition of component is the following. A software component can be defined as a unit of composition with contractually specified interfaces and explicit context dependencies only. That is, a software component can be deployed independently and is subject to composition by third parties. Component model. A component model defines the properties that are common to all components of that model. These properties can refer to the structure of the components, the naming of the interfaces, and the mechanisms for composing components. Often, this mechanism needs to address the way in which components exchange data, such as method call and broadcast, and needs to address whether components can have a state or not. Question. Try to reflect on what are the underlying components of the following examples. These examples are typically used as a metaphor to represent components and composability. The first example is Lego, and the second example is jigsaw puzzles. How does each of these component models address the following properties like composability, reusability, encapsulation, or abstraction? Interfaces. Components can be seen as building blocks with well-defined frontiers, which let third parties compose applications respecting their own needs. From the outside, a component is only seen as a black box through the set of interfaces that it exposes. Interfaces are the points at which components interact with the outside world. An interface is a boundary across which two independent entities meet and interact or communicate with each other. Interfaces partition the functionality into public and private parts. Architecture is concerned with this partition. What should be private and what should be public? In order to define and document an interface, a designer should define the name of a service, the parameters, in particular what inputs and outputs are used, and a contract. This defines the semantics of the computation. What are the inputs and what are the outputs? Well-designed interfaces will enable reusability and evolvability. In various domains, but particularly for embedded systems, it may be important that components specify the dependencies they have on their environment. Let's consider the Facebook app as an example. Dependencies can pertain to other services, or to data, or to some particular infrastructure. As an example of a processing dependency, Facebook depends on a messaging service provided by another component. An example of a data dependency is access to the photo gallery or to a privacy settings file. And for a Facebook app, an example of an infrastructure dependency is network connectivity. Interfaces should be used to explicitly capture this information. They should specify what services the component offers and also what services the component requires. The satisfaction of these dependencies may be checked either at design time or at runtime of the system. As you can see in the example, a single component may have multiple interfaces, and each interface should group together a set of related services. Connectors. Connectors are the architectural building blocks that regulate interactions amongst components. A connector is an abstract mechanism that mediates communication, coordination, or cooperation amongst components. It presents the glue that holds the various pieces of the architecture together. Perhaps the best way to think about connectors is to contrast them with components. The focus of connectors is to enable interaction between components, in particular communication, that is, by transferring data from one interface to another. Another role is to coordinate, that is, to direct or orchestrate the order in which other services are executed. And in the implementation of such coordination, we typically see that the code manages the passing of the thread of execution across other components. Yet another role of connectors is that of conversion. A connector may be used to convert the interaction. It may either transform data from one representation to another, or convert in the execution of some protocol, and then it is often called mediation. Connector types. Different types of connectors exist. In order to get to know these, please refer to the link provided. Stakeholders. Software design is driven by the need of the system to meet the requirements of different people. Each of these groups of people has its own requirements, interests, and needs to be met by the software. We refer collectively to these people as stakeholders. Understanding the role of the stakeholders is fundamental to understanding the role of the architect in the development of a software product. A stakeholder in the architecture of a system is an individual, team, organization, or class thereof having an interest in the realization of the system. Most system development projects include representatives from most, if not all, of the stakeholder groups. The relative importance of different groups will obviously vary from project to project. However, if you do not at least consider each group of stakeholders, you may have problems in the future. You need to balance and prioritize the needs of the different stakeholder groups, so that when conflicts occur, you can make sound, well-reasoned judgments. Stakeholders and their concern. As we stated, any project has a variety of stakeholders. Each of these groups has their own concerns. A customer is the party that pays for a system, has concerns regarding the business goals, the schedule, feasibility and risk, and also product line compatibility. Another stakeholder, like a user, has concerns related to the functionality of the system as well as non-functional properties like performance and security. Yet another category of stakeholders are the service managers. They need to maintain the system and are interested in reliability and availability, amongst others. Stakeholders and their concerns. In addition to users and customers, there's a group of engineers and people involved in the construction of the system that also have concerns. For instance, a system engineer is concerned in requirements traceability, completeness of the architecture, and consistency of the architecture with requirements. Then there's a developer. The architecture definition should be detailed enough to build a system that satisfies the customer requirements, but not too constraining as to preclude different technical approaches. Developers must be able to work independently based on the architecture documentation. Then there's also software maintenance. Maintainers are the people who build source code into binary packets for distribution, commit patches, or organize code in a source repository. They manage the evolution of the system once it is operational, and are mostly concerned with how easy it is to change the system in the future. Future changes must not violate the architecture, and therefore this is a matter the architecture has to support. Many requests coming from many stakeholders. In this slide we show in a different way that there is many different stakeholders that think in different terms when they are confronted with the subject software architecture. The reason for this is that every group of stakeholders has certain concerns of the system from their own perspective. These concerns have something in common, which is the stake of the stakeholder. And we have identified possible stakes, for instance, profit from a business-related perspective of the system, development time, the support for customization, namely the long-term technical aspect of the project. And there's of course usage. That is, after all, the reason why we're building the system. Task of the architect. In the development of an architecture, the architect has several tasks he must address. The most important ones are to understand the priorities of the system. Then there is making of trade-off in design decisions. Thirdly, the architect needs to produce a system abstraction that is complete, correct, and buildable. In doing all of this, you could say that the architect is also a bit of an artist. Whatever representation he comes up with must be beautiful in a way, so that it is easy to comprehend at a glance. The beauty of an architecture can also be assessed by looking at conceptual integrity. The notion of conceptual integrity consists of the fact that things are done in a similar way in various corners of the architecture. There should be one underlying vision about the mechanisms that are used for handling things in a uniform manner. And then in addition to all the technical tasks of the architect, there's the management of politics. Any experienced architect knows that his role involves not just technical ones, but there's also political and strategic tasks at hand. Sometimes he needs to act like a consultant, sometimes to promote and sometimes to unify. What drives software architecture? The main forces that drive architecture design are functionality and quality. Functionality relates to what the system must do, and quality describes the way in which the system achieves these functionality. So you could say the functionality relates to the what, and the quality relates to the how of the system. Typical non-functional or quality requirements are performance, availability, extensibility, and portability. There are other constraints that one should also take into account, such as technical, business, legal, and organizational constraints. An example of a business constraint is a time constraint. This refers to the amount of time available for completing a project. A cost constraint refers to the budget available for the project. Summary. At the end of this lecture, you should know what are the key elements of a software architecture and what are the tasks of the software architect. Also, you should understand that different stakeholders have different needs and that a software architect should elicit and address these needs. The lecture Introduction to Architecture Part 2 is now finished. Thanks for watching.